Howdy! Welcome to Inspire Mountain Academy. I am Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video provides an introduction to z-scores. Let's get started. In previous mini lectures, we've learned about measures of center and variation to describe data sets. We can also describe data sets with measures of relative standing, and the most important of these is the z-score. A z-score is a type of standardized value. It's the number of standard deviations that a given data value is above or below the mean value. By standardizing data values in this way, you can compare values from different data sets more easily. You can also easily identify what part of a distribution a data value comes from. How close is a given data value to the mean? How close is it to the tails? Where exactly is this data value relative to all the other data values in our data set? The z-score quickly communicates all of this information. Now, we can calculate z-scores for both samples and populations. The sample z-score is calculated by subtracting the mean value from the data value of interest and then dividing by the standard deviation. Population z-scores are calculated in a similar fashion. We just exchange sample statistics for population parameters. Now, the convention with z-scores is to round them to 2 decimal places. In all my experience in industry, I've never seen z-scores reported any other way. They've always had 2 decimal places with them. So if you're looking at the graphic here and wondering why the z-scores here are whole numbers, just understand this is just for illustrative purposes to show how z-scores correspond with standard deviations. When it comes to real-world purposes, I've never seen z-scores reported with anything but 2 decimal places. Let's talk for a moment now about how to interpret z-scores. A z-score less than the mean is always negative, and a z-score greater than the mean is always positive. A negative z-score means that our data value resides to the left of the mean value. The mean value, the value in the middle, always has a z-score of 0. Then, if the z-score is negative, we know it's to the left of the mean value. If the z-score is on the right side of the mean, then it's going to be positive. So, just by looking at the sign of our z-score, we know which side of the distribution we're on. Now, the empirical rule that we discussed previously applies to z-scores. So, for ordinary or usual values, values that we would ordinarily expect to see in a distribution, especially if that distribution is normalized, we're going to look for z-scores between positive 2 and negative 2 inclusive. Unusual values will have z-scores above 2 or below negative 2. So, for example, would a pulse rate of 48 beats per minute be unusual if the mean pulse rate is 67.3 beats per minute and the standard deviation is 10.3 beats per minute? Well, we have everything we need to calculate a z-score, so let's go ahead with that. We do that by looking at the definition. Okay, x minus x bar over s. 48 is the value of interest, okay, which we represent with the x. The mean of 67.3 and the standard deviation of 10.3 both appear in our question. So we put those in, and when we punch all that out on our calculator, we get negative 1.87. That means that this value of 48 is located 1.87 standard deviations to the left of the mean value. Now, would this value be unusual? We have to answer no, because it's not unusual, because it's within 2 standard deviations of the mean. So, because it's within this central region right here, the z-score tells us that the corresponding real-world value, 48, is a value we'd expect to see. It's not unusual. Let's return to our POTUS dataset to see more about how z-scores can be calculated. What would the z-score for a U.S. president with a height of 190 centimeters be? Well, first we need to calculate the mean and the standard deviation. You cannot get a z-score unless you have mean and standard deviation. Inside StatCrunch, we can access the POTUS data file and find those statistics. When we do, this is what we get. Next, we use these results to calculate the z-score. We start with the definition of the z-score. So we're going to substitute values into the equation. The 190 comes from the problem statement. This is our data point of interest, so that's going to be our x. Next, the 179.68 is our mean value, which we found in StatCrunch. And the 7.31 is our standard deviation, which we also obtained in StatCrunch. You punch that out and you get 1.41, which is our z-score for a president that has a height of 190 centimeters. Now, how many standard deviations is this? The z-score tells you. I'll give you a moment to answer this question, or you can just guess if you want. I mean, I don't really know the difference because I'm not in your head. Go ahead and make your response. Well, I hope you said 1.41. That is the definition of a z-score. A z-score is the number of standard deviations a data value is from the mean value in the data set. So a z-score of 1.41 means that the associated data value is 1.41 standard deviations away from the mean value. Now, with that in mind, should a U.S. president who wants to be taller want a higher z-score or a lower z-score? And why? Again, I'll give you a moment. Okay, if you want to be taller, then you're going to want a height value that is greater than the mean. So that means moving to the right of the mean value. Scores, the z-scores, okay, to the right of the mean are positive. And the farther they are to the right, the more positive they are. So anyone who wants to be taller will want a higher z-score because that moves him or her farther to the right. And that brings us to the end of this mini lecture. I hope you found it helpful. If you'd like more practice working with z-scores, check out the next mini lecture. And as always, you can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.